And now it's the turn of our second speaker, Mr. José DALLO MOROS. He's the director of the Office of Stewardship, Environmental and Resources at the International Seabed Authority. And in this role, he leads the development and implementation of the regulatory frameworks for the environmental exploration and management of the mineral resources of the international seabed area. So he will share his experience with us, addressing the topic, the use of technology and data sharing in the governance of the area. Mr. DALLO MOROS, please go ahead.
Thank you very much. And it's a pleasure to be here back in beautiful Korea. And I want to thank the organizers, the Ministry of Foreign Affairs of Korea, the International Tribunal, our brothers in Hamburg, and also the Korean Society of International Law. Colleagues, in 1872, the HMS Challenger left Portsmouth with a simple but revolutionary mission to study the deep ocean. The scientists on board measured depth by throwing a lead weight on a rope and waiting for it to touch the seafloor. That was the height of technology at the time. 4 years later, the Challenger returned with the first global database on the deep ocean and some samples of polymetallic nodules. It changed science forever in the deep sea. Today, we're in a completely different world. We can deploy autonomous vehicles to 16,000 meters, receive real-time measurements from glaciers and floats, and even observe the ocean from space. And yet, the core mission is the same, to understand the deep ocean so we can govern it responsibly. In this presentation, I want to show you how the International Seabed Authority is using today's technology and data to deliver on its mandate under UNCLOS for the benefit of humankind. Just for those that might not be so familiar with ISA, we're based in beautiful Jamaica. Last year, we celebrated our 30th anniversary, and we have a quite comprehensive mandate. UNCLOS tells us to regulate the activities in the area designated as a common heritage of humankind. We are a global regulator, and it has worked so far, setting rules and standards using contracts and ensuring compliance and environmental oversight. That's the first box. The second one, also important, is to have environmental stewardship of the deep sea bed. And for that, we use the precautionary approach. We plan and we make regional environmental management plans. We carry out environmental impact assessment with our contractors, and we define standards. For example, currently we're defining environmental thresholds. The third box is key. It is the mission and the mandate to promote science. And that science and data is what is used to define the rules and also is used to protect the environment. And last but not least, there's a duty of benefit sharing, both of financial and not financial resources, and ensure an equitable participation of all, and that means access to the data, training, capacity development, technology transfer, and if mining starts, sharing the benefits of that mining. We almost 170 countries, 170 plus the EU. So far, we have defined 3 types of mineral resources: polymetallic nodules, polymetallic sulfides, and crust. And only exploration has started. We have 31 exploration contracts with 22 contractors. And the area within the area that is currently being explored is less than 1%. We have contracts in the Clarion-Clipperton Zone, the Indian Ocean, the Middle Atlantic Ridge, the Northwest Pacific. And the activity of our contractors produce, I would say, most of the data and knowledge that we have about the deep sea. Why technology and data matters, and why is the core of this presentation. You have I think, 3 good reasons. The first one is the environmental protection. To operationalize the precautionary approach that I mentioned before, ISN states must understand ecosystem structures, resilience, biodiversity distribution, and potential thresholds of harm. None of this is possible without advanced sensors, imaging systems, and continuous data flows. Also, for compliance and monitoring, effective regulatory oversight depends on real-time tracking, anomaly detection, transparency data reporting, and automated alerts from contractors' activities. Also, equity and participation. Because the area belongs to all humankind, data must be shared. Shared equitably, standardized, interoperable, and accessible to all states, particularly developing states. That's why our Assembly approved a Marine Scientific Research Action Plan with 6 priorities. As you can see, one of them is on technology. The other one is on data. And together with that, we have umbrella initiatives that can bring together the science that later the Legal and Technical Commission, a subsidiary body of the Council, can use to inform the proposals they elevate to the political body, which is the Council. We have activities, for example, SKI, the biodiversity assessment, who help establishing solid baselines that are needed for monitoring. We just started a deep sea biobank initiative together with the support of the Korean government to make sure that the samples that our contractors harvest are accessible to everyone in the world, and we can benefit from that and contribute to BBNJ. We have long-term observation and how to do it efficiently, so we can coordinate the approaches and have the same methodology. And something that I think will be relevant as well for BBNJ and others is cumulative impacts. And we keep hearing you cannot look at only one activity, but you need to be holistic and comprehensive. So in terms of technology, we have identified 5 priority areas that we have been working on. One is ocean observation and communication. And the activities include a wide range of technological approaches encompassing satellite data, shipboard measurements, autonomous systems, moorings and lander systems, and submarine cable systems. Ocean observation requires advanced subsea ocean communication for data acquisition and data transfer at large distances through the water column to a surface installation or from a specific site via a cable system. That's the first area we want to prioritize. The second one is monitoring. And we have a hat as a regulator, which includes the online, transparent, and reliable observation of all human activities in the ocean, from shipping to fishery and marine fishing farming to seabed mineral exploration and protection exploration. Solutions that we have identified include, again, satellite data, shipboard measurements, autonomous systems, moorings and lander systems, submarine cable systems, and data dashboards. Third is autonomy, automation, and robotics. Any of the formulated objectives require autonomous, automated solutions, and so do any activities in the deeper water column and on the seabed. Several ISA member countries invested in autonomous systems, AUVs, to better define their continental shelf, and the available systems largely improve rapidly. The developments largely depend on the innovation is connected to the sensor systems that they also developing. Of course, it could not shy away from artificial intelligence and marine learning. It's one of the hot topics today, which represents a new frontier in all ocean activities and aspects of the blue economy. It builds on data obtained by ocean observation and monitoring the collection of key information on the water column and seabed habitats, marine mineral occurrences, and potential natural hazards. AI has the potential to model and predict all aspects of oceanography, geology, mineral resources, biodiversity, environmental effects of all human activities. The last one is the processing. The oceans offer a wide variety of resources, including seabed minerals and wind, wave, and geothermal energy. Should the commercial exploitation start based on adopted environmental regulations, the mining technologies still require innovation. Carbon-free transportation is of key importance. Cost-effective and environmental innovation is also required for the mineral treatment and processing after recovery. Solutions are required for zero-waste approaches and for carbon-free processes. I would like to deep a little bit on some of the examples of the machines which are quite interesting to look at. You can see there a series of smart technologies that are effective and extensive. They use for environmental assessments for the protection of the natural goods, like the seabed, water masses, biodiversity, noise, and other profound requirements that sit in the ISA exploration regulations. The data acquisition and interpretation need tested and reliable technologies to make sure that we have a strong baseline studies. And also monitoring purposes which will involve sensor-based and smart technologies, including automatization, remote surveys, and artificial intelligence, as we saw before. Monitoring of the global oceans has reached the space, and satellites are now just providing a complete bathymetry map of the global seabed with resolutions better than 460 meters, but also provide detailed information on the biological pump and its zooplankton migration from upper mid-water depths by LIDAR sensor technology. Satellites provide critical information on ship movements, oceanography, fish and cetacean migration, atmospheric processes, and the survey of potential natural hazards like earthquakes, submarine avalanches, and volcanism. Mobile instruments used for environmental monitoring are glider and float sensor systems that you can see there in the slide for the regional water column survey of contract areas to collect scientific and mining-specific baseline data, which help us control the distribution of potential plumes, but also navigation and weather forecast. AUVs and ROVs equipped with sensor system are required for the near-field and local survey of activities, as well as for the samples that our contractors carry out. The conceptual design of data access through remote monitoring includes three different aspects: the recovery of fixed assets and the downloading of the data that they host. This, of course, is not in real time. Also, the data collection with a vessel with transmission to shore via satellite and the combination of acoustic and in-air methods for submerged assets would allow real-time transmission and also direct cables to shore, although these are expensive solutions, but allow for a high bandwidth and high reliability applications in real time. In this slide, you can see interconnected USVs, which are unmanned, uncrewed surface vehicles capable to stay offshore for up to 4 weeks and working almost autonomously. They might play a significant role in the monitoring of any marine activities, from fishing to surveying, research, and mining. And all these equipments and technology would give us is data, and data for governance, at least in our case, as a regulator. Data has many benefits. The first one I would like to highlight is that it creates trust. It allows states, observers, and civil society to verify the environmental performance, the compliance with the regulations, and also work together to assess cumulative impacts. Data also enables participation. Developing states gain equal access to our data, to our environmental data baselines, to the submissions of our contractors, and our scientific metadata. This is essential for fairness and credibility. Third, the data sharing reduces the asymmetries. When information is open and standardized, all states can meaningfully participate in decision-making process and the governance of the area. And fourth, it strengthens global coordination. We just heard from our colleague the idea of the clearinghouse mechanism in BB&J, which will be connected to different databases and information produced in other bodies, ensuring coordination. We have a big, deep data base is where we put the data that our contractors provide. Part of it is open. All the environmental data is open. Part of it is confidential, particularly the one related to the richness of mineral resources. But this data, we're trying to also connect to others. We have a connectivity with OBIS, with IOC UNESCO for the biological data. We just did the same with IODI, Ocean Data and Information Systems Catalog. And I think is one of the key elements and lessons learned that we got from the latest UN Ocean Conference. We need more data, but the first step probably is to use the data we already have in place, because data is expensive. And I would like to highlight 4 elements on the way forward, and maybe to further discussion within this audience. The first one is expanding our baseline data coverage. Large areas of the deep ocean are not completely understood. They need broader and more continuous and harmonized sampling, and I will highlight the harmonization. Many people sample with different techniques, with different methods, and this makes very difficult the coordination on their own. In many cases, metadata is missed, so it's not so useful, the data that we have, and this one is a very expensive data. That's why international organizations and the initiatives that we have, as the one I mentioned with the biobank, provide an umbrella to ensure that the methodologies are aligned. For example, in the case of sampling of the deep sea, we're working now on a standard operating procedure to ensure that the methodologies bring together and you can use different samples when you do science. Second idea is the real-time regulatory interfaces. Regulators must eventually receive automated reports, environmental alerts, real-time operational updates. And this is one of the things we stress when working with our scientific colleagues, that we need to put in place systems that are scientifically solid, but at the same time, they are realistic. And the good is enemy of the better. I think that's the saying that you have in English. Third one is the long-term data stewardship. Many of the things we want to assess, like resilience of ecosystem, require long-term data sets. So we should shy away from sometimes the project-based approach. We have a project, 5 years of data, then a gap, then another 5 years. It's difficult scientifically to use that type of data. Then the integration with other frameworks like BBNJ, as my colleague has mentioned, and we are very happy and open to work with parties in the Secretariat of BBNJ in the operationalization of the clearinghouse mechanism. And of course, continue developing capacities and technology transfer. Many states still lack tools to analyze or interpret data, and capacity building must scale accordingly if we want multilateralism to work. Thank you very much.
Thank you very much, Mr. DALLO MOROS, for your contribution. It's really important to understand how the authority uses technology and data sharing when we discuss cooperations and global ocean commons in the deep sea.